Very good afternoon to everyone. I am Shubhangi Rao. I am working as an assistant professor at MLR Institute of Technology, and here I am teaching the subject electromagnetic field for second year AAA students. So today we are going to discuss about Coulombs Law and electric field intensity. So let's start. So how did this law come into the picture? Charles Augustin Coulomb, he actually used a calibrated torsion balance to measure the force between electric charges. This one, or this is the same thing, right? See here, right? Here you can see two charges. This is first charge, this is another charge, right? And he observed few points, right? So what were those points? By using those points, we have got this Coulombs law. So basically, what is Coulombs law? The Coulombs law states that the force between 2 point charges, these point charges are given by Q1 and Q2. So the force between these 2 point charges will be, they act along the line joining the 2 point charges. Here if you notice this and this, right? So they act along the line joining the 2 point charges. Second one, the force will be directly proportional to the product of Q1 and Q2, right? And the third point which was observed by him is that this force will be inversely proportional to the square of the distance between them, means R square, right? So 3 points are like, when the 2 point charges are there at some distance, they will experience some force, and the force will act along the line joining the 2 point charges. It will be directly proportional to the product of these two charges, and it will be inversely proportional to the square of the distance between them. So when we write that in the form of the formula, it becomes when you join it, it becomes F is directly proportional to Q1 Q2 upon R square, right? That is the force. The Coulombs law also states that this force between these 2 point charges, it also depends on the medium in which the point charges are located, and the effect of the medium is introduced in this particular equation, means F is directly proportional to Q1 Q2 upon R square. This effect of this medium is introduced in this equation of the force as a constant of proportionality. We wrote formula in this form, right? So when you remove this proportionality sign, you get one constant K here in place of that. So it becomes F is equals to K Q1 Q2 upon R square, where K is the constant of proportionality and the value of K is equals to 1 upon 4 pi epsilon, where epsilon is the permittivity of the medium in which charges are located, right? And if you talk about this unit of epsilon, it is farad per meter, right? So this epsilon can be written as epsilon naught epsilon r, where epsilon naught is the permittivity of free space, or it can be called as the permittivity of vacuum. Epsilon r is the relative permittivity, or you can call it dielectric constant of the medium with respect to free space, right? And this epsilon, which is equals to epsilon naught epsilon r, it is nothing but absolute permittivity, right? So we understood the formula. F is directly proportional to Q1 Q2 upon R square. When we remove this proportionality sign, we get a constant K, which is a constant of proportionality, and the K is equals to 1 upon 4 pi epsilon. Epsilon is the permittivity of the medium, where epsilon is equals to epsilon naught epsilon r. Epsilon r is the permittivity of free space or vacuum, and epsilon r is the permittivity of the medium, right? Now, you see here, for the free space or the vacuum, the relative permittivity will become epsilon r is equals to 1. As we know, epsilon is equals to epsilon naught, epsilon r. So when we have the medium which is free space or the vacuum, that time the value of epsilon r will be equals to 1. So we get epsilon is equals to epsilon naught, right? And it can be written as f is equals to 1 upon 4 pi epsilon naught q1 q2 upon r square, right? The value of this permittivity in the free space means the value of epsilon naught is equals to 1 upon 36 pi into 10 to the power minus 9. When you solve it, it becomes 8.854 into 10 to the power minus 12 farad per meter. When you further solve it, when you combine it, it becomes k is equals to 9 into 10 to the power 9, right? So now we can write this formula as f is equals to q1 q2 upon 4 pi epsilon naught r square, right? This is the formula. So this is the force between 2 point charges which are located in the free space. You can understand it by we are taking epsilon naught. Now if we talk about unit of epsilon naught, in the previous slide only we have discussed, it will be farad per meter, right? Next, vector form of Coulombs law, right? Now in this diagram you can see we have two charges q1 and this is q2, right? This is the distance between these two, r, okay? So we are writing r12. So this is 0.1, this is 0.2, or you can say it as charge 1, charge 2. So the distance between them is r12, right? So we can write this formula as f is equals to q1 q2 upon 4 pi epsilon naught r12 square, and the unit vector will be a12, right? So a12 is the unit vector along r12, and what is r12? It is vector r12 upon magnitude of r12, okay? So a12 is equals to r12 upon mod of r12. What is r12? Basically, if you consider the origin, so this is r2, this is r1, right? So it becomes r2 minus r1 upon mod of r2 minus r1, right? Where the r is the distance between these two charges, right? Now if you put that into this formula, it becomes q1 q2 upon 4 pi epsilon naught r12. Here we are writing for force on 2, here this is force on 1, so it becomes, in place of r12 it becomes r21. Again the remaining things would be same, the only difference will be like r, here it will be r1 minus r2 divided by, it will become mod of r1 minus r2. So r12, so r1 minus r2 is equals to minus of r2 minus r1. So basically if you write in the form of unit vector, it becomes a21 is equals to minus of a12, right? So here f1, here in this place of f1, in place of a21, I can write minus a21. So it will become minus f2. So basically what we understood from here is f1 is equals to minus of f2. Magnitude is same, the only difference which is there is the direction is changing. One is in this direction, another one is in this direction, but the magnitude is same. For example, f1 is force on q1 due to q2, f2 is force on q2 due to q1, right? There are some more points which we must know. The first point is like the charges, the like charges, they repel each other while the unlike charges attract each other. Meaning of this, if you have both positive charges, suppose plus q1 plus q2, so the force will be in the opposite direction because they are repelling each other. You can see here. Similarly for negative charges also, because they are same, so they will be repelling each other. If the charges are not same, means one is positive charge, another one is negative charge, so they will attract each other, right? So if you notice here, the force are in again different directions, but they are towards each other, right? Also, it is necessary that these two charges which we are considering to calculate force, they are point charges, they must be point charges, and they must be stationary in the nature, right? The two charges, the 2 point charges may be positive or negative, right? So, their signs must be considered to calculate force which is exerted. Another thing which we must know is the Coulombs law is linear, which shows that if any one charge is increased by n times, then force which is exerted will also be increased by n time, right? So, F1, because of that n time increment, it becomes NF1, it can become MF2, right? Similarly, if here we have written this equation, F2 is equals to minus F1, because of the increment of n times, the force will also become incremented by n times. So, n F2 is equals to minus n F1. N is nothing with the number, it's a scalar quantity. So, till now we had discussed about the two charges. Now, if you have more number of charges, in this example you can see you have 4 charges basically. The first one is Q. There are another 3 charges also, Q1, Q2 and Q3, right? So, basically we are finding out the force on Q due to Q1, Q2 and Q3. This is the origin. From origin we can have the distances. So, from origin to Q we have distance R, from origin to Q1 the distance is R1, from origin to Q2 the distance is R2, and from origin to Q3 the distance is R3, right? Also we have unit vectors. For this Q3 the unit vector is A3Q, for charge 1 the unit vector is A1Q, and for charge 2 it's A2Q. Now, the first force we have written here, the force on Q due to charge Q1. So, this can be written as Q1 into Q divided by 4 pi epsilon naught R1Q square, and unit vector is A1Q. A1Q is R minus R1 upon mod of R minus R1. Similarly, we are writing the force on Q due to Q2. It will become Q2 into Q divided by 4 pi epsilon naught R2Q square, and unit vector is A2Q. A2Q is R minus R2 upon mod of R minus R2. Similarly, force exerted on Q due to Q3 will be written as F Q3Q, means Q3 into Q upon 4 pi epsilon naught R3Q square A3Q. Again, A3Q is nothing but R minus R3 upon mod of R minus R3. So, when we want to find out the total charge on Q due to Q1, Q2 and Q3, it can be written as like this. FQ is equals to FQ1Q plus FQ2Q plus FQ3Q. Now, based on this concept which we have discussed just now, we may have some problems also. So, this is the step-by-step approach to solve the problems to find out the force, right? So, first step is whenever any problem is given, first we need to obtain the position vectors of the points where the charges are located, right? After getting the position vectors, next step is to obtain the unit vectors along the straight line which is joining the charges. So, the direction is always towards the charge on which the force is exerted or which is to be calculated, right? Step 3 is, by using Coulombs law, we can express the force which is exerted in the form of vector. Step 4 is, if there are more charges, we have to repeat the same steps, right? Because each charge is exerting a force on the charge under the consideration. Then step 5, by using principle of superposition, we can sum up all the forces, right? Whatever we have calculated, for example, in the previous example which we have seen, we had 3 charges. So, this equation shows the total value, right? So, we are basically applying the principle of superposition. So, by getting all the answers from the previous steps, we have to vector sum of all the forces to get the total force on that particular charge, right? So these are the steps to be followed to solve any numerical problem. Now we are going to discuss about electric field intensity, right? So before understanding electric field intensity, first we should know what is electric field, right? So basically electric field is an elegant way of characterizing the electrical environment of a system of charges. Here if you see in these diagrams, you have various charges, right? Various forces are applied, right? So basically the electric field is a way of characterizing the electrical environment of a system of charges, right? So what is electric field? Basically what electric field we can understand by electric lines of forces, right? Here you see various charges will be there, right? Field lines will be there. So basically electric lines of forces, they start from positive charge, right? And these lines terminate on the negative charge, right? So electric lines of forces start from positive charge and terminate on negative charge. If negative charge is not found, they will terminate on infinity, right? Also, more number of charges, more field lines, right? Another property is the field lines will never cross each other, right? Also, the field line spacing indicates the field strength. So, for example, means suppose this area, if you see here, the lines are very nearby to each other. So, here the field is strong, right? It is near to charge also. But if you notice here, a lot of space is there between them. So, here the field is weak. So, by understanding the field line spacing, we can understand what is the strength of the field, right? So, field line, they start from positive charge, they terminate on negative charge. If negative charge is not found nearby, they will terminate on infinity. More number of charges, more number of field lines, they will never cross each other. Also, the spacing indicates the electric field strength, right? So, this is about electric field. Now, what is electric field intensity? A few slides back, we have discussed about the force which is experienced by one charge due to another charge, right? For example, we have two charges Q1 and Q2. So, for example, Q2 is experiencing some force due to Q1 or Q1 is experiencing some force due to Q2. So, that force, how we wrote this force, it is Q1 Q2 upon 4 pi epsilon naught R12 square. Basically, Q1 Q2 are the two charges. There is some space between them, distance between them. So, the force on Q2 by Q1 is written as, or the force on one charge due to another charge can be written as F is equals to Q1 Q2 upon 4 pi epsilon naught R12 square, and the unit vector is A12. It can be written as R21 square and the unit vector can be written as A21 also for F1, right? Now, if you divide one charge by this F2 upon Q2, it becomes Q1 upon 4 pi epsilon naught R12 square A12. So, by this formula, what we are understanding, by this arrangement, what we are understanding? We are understanding that the force exerted per unit charge, the force exerted per unit charge is called electric field intensity. In simple language, force per unit charge is called electric field intensity, or it can be called as electric field strength. So, this electric field strength or electric field intensity is a vector quantity, right, and is directed along a segment from charge Q1 to the position of any other charge, right, and it is written by E. So, E is equals to basically Q upon 4 pi epsilon naught R square A. A is the unit vector, right. So, here we have taken P. So, P can be the position of any other charge like 2, 3, 4, 5, 6 and number of charges, right. So, this is the formula for electric field intensity. right? E is equals to q upon 4 pi epsilon naught r square AR. In spherical system, you can write it like this. The unit vector becomes AR, right, along the radius of the sphere. Here if you see, we are writing E is equals to force per unit charge or force upon unit charge. The units are Newton and Coulomb. So the unit of E is Newton per Coulomb, right? It can also be measured as volts per meter. Next, if you have n number of charges, then how would you write the formula for electric field intensity? If you see, there is a position, right, of any charge, some more charges q1, q2, q3, q4 up to qn are there. So obviously the field exerted will be E is equals to E1 plus E2 plus E3 plus E4 up to En would be there, right? So E1, as per the formulas which we have discussed in the previous slide, the formulas for example E1 is q1 upon 4 pi epsilon naught r1 r1 square, AR1 plus due to E2 it's q2 upon 4 pi epsilon naught r2 square AR2. Similarly up to n you write, okay. Then you write this formula combinedly and you can write it as E is equals to 1 upon 4 pi epsilon naught sigma I is equals to 1 to n, or in place of n, for example, the maximum charges are 6, so you can write it as I is equals to 1 to 6 q upon ri square, qi upon ri square ARI, where I is the again 1 to n, right? This is unit vector, so it is equals to Rp minus Ri upon mod of Rp minus Ri. Again, from one position to what is the position of next one, you can find out this unit vector, right? Some few more points are there which must be kept in the mind when we are dealing with the electric field intensity. The first one is the electric field around a charge q1 is directly proportional to charge q1. Next is electric field around a charge q1 is inversely proportional to the distance between charge q1 and the point at which E is to be calculated, right? So more is the distance, less is the electric field intensity, because it is coming as denominator, right? Less will be the force experienced by the unit charge placed at the point, right? Next is the field intensity E at any point and the force F exerted on the charge which is placed on the same point. They will always be in the same direction. For example, this particular charge E and F, they will be in the same direction. Next point is placing unit charge is a method of detecting the presence of electric field around the charge. So without any unit charge, unit test charge placed nearby, every charge has its electric field. It is always existing around it, right? Another one, the test charge which is placed, it must be small enough so that the electric field intensity E to be measured should not get disturbed, right? So these are the 5 points, 5 observations which we must consider, right? Next we'll discuss about the charge distribution, right? So basically we have 4 types of charge configurations: point charge, line charge, surface charge and volume charge. Point charge, if its dimensions tends to 0, it becomes point charge like this. If you talk about line charge, this is line charge. If charges are distributed on a line uniformly, that is called line charge, and this kind of distribution is called uniform charge distribution. The another one is this one, surface charge. So the charges are distributed on a surface uniformly, that is called surface charge, right? And this distribution is called uniform charge distribution. Next one is volume. So that when the charges are distributed in a volume, that is called volume charge, right? So if we discuss about the line charge, we should also discuss about line charge density. Similarly, we should discuss about surface charge density and volume charge density. So line charge density is given by rho L, surface charge density is given by rho S, and volume charge density is given by rho V. So basically what is volume charge, what is line charge density? So the line charge density is charge per unit length, right? The unit is Coulomb per meter, right? If you talk about surface charge density, rho s is equals to charge per unit surface, right? Unit is Coulomb per meter square, and this is charge per unit volume, and the unit is Coulomb per meter cube, right? So from this also you can find out charge. Q is equals to, it will become line integration of rho L dl. For surface charge density, Q becomes surface integration of rho s ds. This is double integration, this is single integration. And volume charge is Q is equals to, for volume charge density, we can find out Q by using the formula. Q is equals to volume integration of rho v dv. And here this integration is triple integration, right? So this is about charge distribution, point charge, line charge, surface charge and volume charge. So why we have discussed about this charge distribution? Because we can find out electric field intensity due to various charge distributions. So first we are going to discuss about field due to infinite length line charge, right? For this, for understanding this, we have taken this system where you can see three axes which are perpendicular to each other. This is x, this is y and this is z. Okay. For this even we can consider a cylinder also. So this becomes r, y or r, they are in the same direction. X would be common, z would be common, right? So we have taken, what we have taken here on z axis, we have considered a small element, differential length, which is given by dl, right? And due to this element, we basically have to find out field intensity on this point P, right? So that is how we can join this. And the distance between these are r, capital R. This length is small r. The angle between z and the line joining differential element and the point is given by theta, right? So this rho L will be given by dq upon dl. So from here you can find out dq is equals to rho L dl. So basically here this L, it is in z direction. So in place of dl we can write dz. So dq is equals to rho L dz. The coordinates of dq are 0, 0, z, means on this element some charge is there, because we have considered this element where the charges are distributed. So the coordinates will be 0, 0, z. The element of y and x is not there, only z is there, so it becomes 0, 0, z. And the coordinates of this point P will be, here if you notice, only r is there or y is there, so it becomes 0, r, 0, right? So now because we have coordinates of this point and this point, so we can find out the value of r. So it becomes rp minus r. This point is, for example, dl. So from here to here we are counting, right? So this will be this minus this. So it becomes rp minus r dl, which is equals to ray or yay minus zaz. And its magnitude would be under root of r square plus z square. By using these two, you can even get unit vector, which is equals to ray minus zaz upon under root of r square plus z square. And the formula of this electric field intensity D is equals to dq upon, because here we are taking D because we are taking differential elements dq, dl, so D. So D is equals to dq upon 4 pi epsilon naught r square. Basically this has come from the formula E is equals to q upon 4 pi epsilon naught r square ar. So we are writing dE is equals to dq upon 4 pi epsilon naught r square ar. Now we will put the value of r and the unit vector in this formula, and it becomes this. In place of dq, from this equation we are getting dq is equals to rho L dz. So we are putting all of the things in this formula and we are simplifying it. Okay, now we have removed this differential D, and now because we want the total value, so we will use this integration sign, and we know the range is between minus infinity to plus infinity. So we are putting minus infinity to plus infinity. Remaining things are same. We have simplified it. So it becomes rho L upon 4 pi epsilon naught in bracket r square plus z square to the power 3 by 2 r dz ay. Right. Now we have to make some modifications here. See, for z is equals to minus infinity, if you want to find out this theta angle which was here, if you see in the previous slide, this one, there will be few changes in this. It becomes tan inverse infinity which is equals to minus pi by 2 means minus 90. Similarly, for z is equals to infinite, it is plus 90. So now here in this integral limit, in place of minus infinity to infinity, we are going to put minus pi by 2 to pi by 2, and also here it will change. In place of z, we are going to write tan. So it becomes tan square theta. So the overall formula is now becoming rho L upon 4 pi epsilon in bracket r square plus r square tan square theta to the power 3 by 2. And here also we will simplify. So it becomes r into r sec square theta d theta ay. So when you simplify this entire equation, you get the final answer as rho L upon 2 pi epsilon naught r ay. Why? Because in this direction, right? Here these elements would be cancelled due to symmetry. So you will have the element only in this direction. So we get y or ar, because in this direction only we had r also. So this formula becomes rho L upon 2 pi epsilon naught r ar also, and the unit is volts per meter. Right. So this is the field due to infinite length line charge. Next, we can consider in place of line charge, we can consider a sheet of charge also. So now we will find out a field due to sheet of charge. So if you see in this diagram, the sheet is in which plane? It is in xy plane. This. Right. So same as in the previous derivation, we have considered a small element differential length on z-axis. Here we have to consider a small surface area on this sheet, right? Similarly, same as the previous derivation, here we can find out dq, which will be equals to rho s ds, right? Or it will become rho s is equals to r dr d phi, right? So if you simplify it, now the formula is d is equals to dq upon 4 pi epsilon naught r square ar. You have to put the value of dq here, so it becomes rho s r dr d phi upon 4 pi epsilon naught r square ar. Okay, unit vector, we have to put this value because basically we are finding out the field intensity on this point due to the sheet of charge. So same as the previous derivation, we need to consider the coordinates here. We need to find out the value of r, which we get as this minus rar plus zz divided by under root of r square plus z square. So we need to put it in this formula. When we simplify after putting each and everything, we get the value is rho s upon 2 epsilon naught an. So if you notice here, if you compare this formula with the previous formula, here you had one term r also, but here it does not depend basically on the distance between this point where we are finding out the field and the sheet. The only thing which we need to take care is the direction, unit vector, right? So E is equals to rho s upon 2 epsilon naught an Vn, right? V by m. So just like sheet of charge and infinite line charge, we can find out field due to point charge as well as volume charge also. So in this table you can see due to point charge, the field intensity in volt per meter is q upon 4 pi epsilon naught r square ar. Due to infinite length line charge, just now we have calculated, it is rho L upon 4 pi epsilon naught r ar. Due to infinite sheet of charge, we can see it's rho s upon 2 pi epsilon naught an. Due to volume charge, it will be integration of rho v dv upon 4 pi epsilon naught r square ar. Right, so this was about electric field intensity, Coulombs law, and the field intensity due to various charge distributions, right? So thank you very much. In case of any doubt, you can write to us. Thank you very much once again.